Okay, all right, let's start, okay? So, rainy days. Let's see, where are we last time? Okay. So, if everybody remembers, we talked about last time several very simple cases of demonstration simulations about random forest and boosting, right? The very simple case simulation we see last time. Oh, sorry. Involves two kind of boundaries. The first kind of boundary is a. So the first kind of boundary we see last time is a linear boundary, right? So this is x1, x2. Then we have a linear boundary like that. Let me actually. It's much better. Right, for the linear boundary, the logistic regression performed the best. Whether it's trees or random forests or boosting, do not really compete with the true logistic regression because the logistic regression actually is the true model. The true decision boundary is linear. If we have a decision boundary that is nonlinear, in this case, we also see that we can do a logistic regression that performs pretty well. And in order to do this regression, basically we have this model that probability y equal to 1. Remember, the logistic regression is this probability is a sigmoid of beta x, right? Now, this can be just a simple linear model where it's beta 0 plus beta 1 x. In this case, we have x1 and x2. So it's beta 1 x1 plus beta 2 x2. So if we write it this way, that gives us a linear decision boundary for logistic regression. How do we generate this type of decision boundary for logistic regression? It's also the same thing. We just make it polynomial, right? Okay, so just the probability y equal to 1 is the sigmoid of beta 0 plus beta 1 x1 but plus beta 2 x1 squared, right? Plus beta 3 x2 plus beta 4 x2 squared. So basically add the square term, and in that case, if you do the logistic regression, it actually gives you a decision boundary like this, right? A circle decision boundary. Square term of logistic regression that will separate the data pretty well. But this is already after you have looked at the data, right? Now, if your x is very high dimensional, if you have 50 dimensional x, 100 dimensional x, then how do you ever decide what kind of polynomial to use for logistic regression? Okay, so the same problem for linear regression. Right? So it's almost impossible for you to decide. Now, on the other hand, you can always do a tree and a random forest and a boosting, because these are natural models that capture the nonlinearities in the data, right? Okay. So that's why we begin today by looking at a Polish bankruptcy data. The data is okay, so this is real data come from Poland, where we have 5,630. We have about 6,000 banks, and companies, just companies. But then we have their bankruptcy data. Okay, so out of these 6,000 companies, about 7% of them has bankrupted over the last or during the time period we're studying. And for this data, we have 56 variables, because these are mainly financial ratios for financial indicators for these companies. Okay, the data source if you want to interested in the data source, you can just go and download here. The period we analyze is from 2000 to 2012. Okay, all right. So here are all the variables, right? It's very hard to list all of them. But here are the variables x1 to x30, mainly all kinds of financial ratios we can get for these companies. Okay. All right, all the way to 63. Okay. So we have so some variables are missing. Right? So there are 63 variables listed here, but actually our data contains 50, 60 different variables. Okay. So the first thing we do, we create a training and we create the test data. One way to do this is to randomly split the data into traits. Just randomly take 7. So here we take 70% for training, 30% for test. So one way to do is just randomly sample 70%. But that's not a good idea in cases like this, because there is only 7% of the firm that has bankrupted. So if y equal to 1 means bankrupt, y equal to 0 means not bankrupt, we have only 7% of the data has y equal to 1. So that's a problem, because if you just randomly pick 70% of the data out, your training data may contain, or especially your test data, which is only 30%, may contain almost no y equal to 1. Okay, so the y equal to 1 may be very unbalanced in your training and your test, right? So ideally, you want to randomly select your sample, but at the same time, you want to guarantee that there's 70% here, there's 7% of y equal to 1 here, and 7% of y equal to 1, right? Now to do that, we need to do some kind of balanced sampling, right? Not just totally random. But we do random sampling, but at the same time, we guarantee that there's about 7% of y equal to 1 in each data set we create. So in other words, unfortunately, there's a very nice command in R for you to do that. From the carrier package, you can do create data partition that will automatically guarantee that the random sampling result is also balanced with respect to y equal to 1. So here's we test it, right? So we see, okay, what is the number of bankruptcy in training data? How much is in the test data? It's all 7%. Okay, so that's very balanced. Okay, so again, we first try logistic regression. So we're just going to predict bankruptcy. So bankruptcy is a 0-1 variable. We're going to regress bankruptcy on all the 56 different, actually 55, I'm sorry. So one of them is y, right? So 55 dimensional x, we're going to regress all of them. And doing logistic regression. And here's the result, okay? The first thing we know is that none of them are significant. Because we have 55 different variables. You try to regress them, all of them are insignificant, okay? So none are significant. And so basically means if you do regression like this, and you want to know which factor are, quote unquote important, you discover none of them are, right? Because, well, one of the reason for this is because a lot of variables are highly correlated with each other. So there's a serious multicollinearity issue once we have so many variables, and all of them are basically financial ratios of a company. So highly correlated. It's very hard to separate them, and so everybody becomes insignificant. Okay, as a result. So regardless of if everything is insignificant, that makes it very hard to interpret. Right? So what is the important? What is not important? What are significant? What are not significant? Very hard to interpret. But regardless of interpretation, suppose you say, I'm not interested in interpretation. I just want to know whether the model predicts bankruptcy well. Okay? So to know that, to answer that question, we put the data onto the test data. Okay. So in the test data, we see that this is our y hat. This is the true y. Okay. So these are the mistakes we make, and the error rate is about 8.5%. It's not that bad. Well, is it? I'm not sure. Okay. Is it bad or is it good? 8.5% error rate. Is it good or is it bad? Maybe it's very bad. In this case, I think it's very bad. I'm sorry. It's not pretty good. It's actually very bad. Why? Because the bankruptcy rate is only 7%. So again, I can have an extremely stupid predictor that says everybody is not going to bankrupt. Right? I just have a predictor that says nobody is going to bankrupt. Okay? And it will only make 7% mistake. And right now we have 8% mistake. Okay? So this logistic regression is worse than a predictor that simply says nobody ever bankrupts. Right? Okay? So this is actually a pretty bad result. All right, let's try classification tree. Okay? So I'm going to build a tree now using the rpart package. Again, the way to do it is rpart, building a tree with bankrupt as a y variable, all the other variables as x. Okay? And I'm going to build a large tree and prune it. And so prune it back. And the final result is, again, 7.2%. It's slightly better than logistic regression. But it's still almost only as good as a predictor that says nobody bankrupts. Okay? So it's still not very good, but it's better than logistic regression package. All right. Now let me try random forest. Okay. So here I have 55 different variables, and when I do random forest, I use the camera function to help me train it, So basically, I train the method by trying all kinds of different. So in random forest, we need to try what? What do we need to try? What do we not know? If we just do backing, right? If we do backing, then we consider all variables every time we split. Okay. However, when we do random forest, remember every time you split, we only consider a subset of the variables. But how many? How many do you consider every time? There are 55 different variables. Every time you split, right? There are 55. So every time we split, you can consider maybe one variable, maybe 5, maybe 10, maybe 55. We don't know how many every time. What is the optimal number to consider every time? So in order to find it out, we tune it. Okay, we tune it. And the reason, what I mean by tuning is we try a lot of different these, right? We try 1, 5, 10. We try all of them, and all of them we put it on using cross validation to find out the cross validation error, and we pick the minimum cross validation. So that's called tuning. So here's what I do, right? So I use the train function to help me tune, and I say tune length equal to 10, which means that the function will automatically generate 10 different number. So this is called mtry. Mtry means the number of variables to consider every time. So the tune length equal to 10 will automatically generate 10 different mtry numbers. All the way, from 1 to 55, it will pick about 8 different numbers along the way. Okay, so the minimum is 1, the maximum is 55, and then we'll pick 10 numbers, and then they will try and find out what is the best mtry number. So here's the result. Okay, this is accuracy. So as we increase the number of, so this is 1, right? So here this means every time we split, we only consider one variable. So we just randomly pick one variable, and that's it, right? On the other hand, this is the 55, which means every time we split, we consider all 55 different variables, right? So that's backing essentially. As we decrease the number, our accuracy actually increases, or our cross-validation error goes down. But then, of course, if you decrease too much, then your cross-validation error go up again. So here the accuracy goes down again. So the optimal point is here. Okay, so this is the optimal number of variables to consider every time. And it turns out that the optimal one is 43. So every time we consider 43 variables out of 55. What is the result? Okay, so once we use the optimal model, we're able to generate a test error of 6%. So we're getting a little bit better. Right? We're getting better than a predictor just says everybody no default. Okay, everybody no bankrupt. Okay. But we try really hard to get there, right? So it's one of the things about this data set is it's very hard, okay? It's very hard to predict such a small number of bankruptcy rate using 55 variables that are highly correlated with each other. It's very hard to do. Okay, so finally we tried boosting, all right? So again, I use, so I do not write the train function, but I directly give you the boosting command. So to do boosting, we use the GBM function from the GBM package in R. The GBM stands for gradient boosting. Okay, gradient boosting. But gradient boosting, we haven't talked about gradient boosting in this class. But gradient boosting is just boosting. Okay, it's a boosting technique, or it's a boosting model that we haven't discussed. But it's the same in spirit. All right. So GBM bankrupt all the other variables. Here the distribution is ADA boost, meaning we're using the ADA boost algorithm. And we grow 5,000 trees, meaning 5,000 iterations. In each iteration, the depth is 10 depth trees, and the shrinkage equal to 0.1. Okay, so every time when we add the tree, we add only 0.1 of the tree into it. So all of these parameters have already been tuned, meaning I have already selected these parameters running something like a train function to help me select the best combination. Okay. If I do that, what is the test error of 5%? So it turns out that 5% is as best as I can do using tree-based methods. Maybe there's some other methods. I'm sure the other methods can go down even more, but 5% is the best we can do. Okay, using tree-based. Okay, so basically doing this, we decreased we increased our accuracy from 80% error term down to 5% error. Then the question is, how do you? Okay, we have improved our prediction accuracy, but what does it actually mean? Right? I'm interested not only in predicting, but I'm also interested in interpretation. I want to know what are the variables that are important to help me predict bankruptcy, or most correlated with bankruptcy. So in the linear model, you can look at a p-value, and then you can say, okay, whatever is significant. But as we already see, when you do logistic regression, none of them is significant. It's very hard to do, right? Okay, so in that case, how do we evaluate the importance of variables? Many people who are unfamiliar, so there's a very popular misunderstanding about things like tree-based method, because you will hear people say this a lot. People will say random forests are a black box, meaning that you cannot interpret it. It's a prediction machine. So you put the X in, it will give you a Y prediction, but nobody knows how to interpret the model. If you do a linear regression, it's very easy to interpret, right? So. Okay, so if you do a linear regression, y equal to beta 0 plus beta 1, x plus e, then what is the effect of x on y? Right? So the effect doesn't mean causal effect. Okay, just statistically, what is the effect of when you increase x by 1 plus 1, how much does y increase? Well, y increased by beta 1. So beta 1 is the effect of x on y, so it's very easy to read or interpret, right? But if you do random forest, how do you interpret the effect of, how do you interpret the model? That's the question. Many people believe that it's impossible to interpret things like random forest because it's a black box, and that is totally wrong, okay? Because it's actually not that hard. So any model, any nonlinear model, is basically y as a function of fx. If we're doing regression, it's something like that, right? So what is the effect of x on y? It's very easy. It's the derivative of fx with respect to x. That's it. Okay? So in the linear model, what is this derivative? It's beta 1, right? But for nonlinear model, can you calculate this? Of course you can calculate it. It's very easy. Just, if you given any x value, suppose I want to evaluate this at x equal to 1. How do I do it? Well, at x equal to 1, I compute what is f1, and then what? And then maybe I put epsilon, okay? Minus f1 divided by epsilon, and that is the derivative, right? Okay. That's it. It's really simple, and that tells you the effect of x on. It tells the effect of x on y. So that's true for any nonlinear model. That's true for any model. Okay. So in other words, it's not really that hard to interpret. It's just that you need to do additional steps of computation. Now, if x is multidimensional, if f is multidimensional, it's not a function of x. So here I'm assuming x is one dimension, right? But what if x is multidimensional? What if it's x1, x2? Okay, if that's the case, what is the effect of x1 on y? Well, in that case, this is actually direct derivative, but in this case, it become a partial derivative. So it's really x1, x2 with respect to x1, right? So there are two ways to do it. One way is to fix x2. Fix x2. As only consider the derivative of this function with respect to x1. So we can fix x2 at, for example, the mean x2, right? Just fix x2 at its mean value, and then compute the derivative of this f with respect to x1. And by the way, in one dimension, if x is one dimension, when you do this, you end up with so in the linear model, the effect of x on y is always beta 1, regardless of the value of x. In the linear, in the x, right? So potentially what you can do is, this is x, then the effect, the so-called effect, actually changes with the x. Okay? So this is basically df dx. So it's it changes with x. It's not a constant. But if in two-dimension or multi-dimension, you can always fix x2 at some value that you like mean x2, And then you can calculate this for the entire x, right? x1. Okay. But what if I do not want to fix x2? I just want a total effect of x1. I don't want to fix x2. Okay. Well, that's also easy. You just take an integral, right? So you just fix x2 one at a time, and then you integrate with respect to x2. Okay. Right? Px2, dx2, and that's it. Okay. Just integrate it, and give you the total effect of x1 on f. So you can do something like this too, where each point is an integration over all the other x2 values. How to do this integration? In using data. You can typically, if your data is large enough, then you can approximate it as this x1, x2i, where it's each data point, divided by x1, the summation of I equal to 1 to n of it. So in other words, you can always replace the integral with a mean when you are doing infinite, when you on finite data sample. Okay, you will always replace that. That's Monte Carlo integration. I think I talked about before. But if you don't understand, it's okay, because you can always replace. Just remember, right? You can always replace the integral with the mean, and you can calculate this. So it's all very easy in principle. Okay. Now, luckily, you probably don't have to do it yourself, because a lot of these packages have already written these functions for you. All right. So in terms of bagging and in terms of random forest and boosting, typically what people do is they do variable importance and they do partial dependence. What I mean by partial dependence is exactly this. Okay. So here we see is y as a function of variable 39. Here we see as y as a function of variable 46. Why these two variables, I'll explain in a second, but this is basically the derivative of the f with respect to attribute 39 and integrate over all the other variables. Okay? And it has this kind of relationship. And here is the derivative with respect to this variable, integrate over all the other variables. So this is called a partial dependence plot. And the function will automatically do it for you. What this is called a variable importance plot. Now the variable importance is computed slightly differently. The variable importance is because we have a tree kind of structure, right? So the variable importance is computed by, for each tree, I go from the roots down, and I see every time I make a split over a certain variable, how much do my error decrease? And that is a measure of how important that variable is. And then I average over all the trees in Ensemble, because we're doing random forest and boosting, so we have Ensemble. So I average over all the trees in the Ensemble, and I will look at and I'll basically rank variables in terms of the ability to decrease the error of my model. So that's called variable importance. And here's the result. Okay. So in our model, we have again 55 different variables. But the most important variable are variable 39 and 46. These are the most important variables. But what are they? Okay? What are 39, 46? Let's take a look. 39. Is it 39? Is it? I forgot. 39, 46, right? Yeah, okay. What is 39? 39 is profit on sales divided by sales. Okay? So it's basically profit divided by sales. Okay? And what is 46? Current assets minus inventory divided by short-term liability. Do people know what this is? So current assets divide, essentially current assets, right? No inventory, but current assets divided by short-term liability. What is it? The first one, okay, the first one is basically the margin of profit, right? Your profit divided by your sales is basically your profit margin, okay? The operating profit margin. The second one, for those of you who are not familiar with corporate finance or accounting, this is basically the quick ratio, okay? Short-term liability divided by current assets divided by short-term liability. Okay. All right. So what our model tells us that in order to predict bankruptcy, the most, at least the first two, right? You can take a look at all the other variables, but the first two most important one, 39, 46, are basically the operating profit margin and the quick ratio. So these two are the most important variables. And then we can do the partial plot, okay, partial dependence plot, to figure out the relationship between these ratios and the bankruptcy probability. So what this plot tells you is that as we increase the profit margin, our bankruptcy probability will go, I don't know why it goes up like this, right? But then it will go down like this, okay? So it will go down in this trend, and so there's an abrupt drop-off. So once my profit margin goes goes from negative to positive, my bankruptcy probability decreases like that. Okay, so if I have a positive profit margin, then my bankruptcy rate will suddenly drop. Now, on the other hand, the quick ratio is a continuous decline of. So as we increase the quick ratio, so as we increase our current assets with respect to our short-term liability, my bankruptcy rate will decline slowly and slowly, right, like this, okay, until it's no longer able to decline. So this is what the partial dependence plot can tell me, the relation between different variables, right? Okay. All right. Now this is a case of using tree-based methods to do classification. Bankruptcy is a 0-1 classification variable. Now let's try to do regression. Okay. For the regression, we try the Boston housing price. Now previously we already seen this data set when when I'm simply doing a stump. And then aggregate a stump together. But now let's actually properly do it, right? So again, we split the sample into training and test, and I'm going to run a linear regression of median house value, all the other values. So this is a data set where it contains housing value and it contains all socio-economic variables and the housing, how many bedrooms in the house, etc. It contains a lot of variables like that in a neighborhood in Boston. So I'm going to try to predict the housing value, right? So I'm regressing median house value on all the other variables in the data set. Okay, what is my error? Right? How good do linear regression do? Well, linear regression has an error term of 21.89. Okay, so that's the L2 loss error. 22. Okay, 21.89. Okay, and these are the variables that linear regression tells us are statistically significant. Crime rate, so this is a crime rate will significantly decrease the housing value. I don't know what ZN is. In fact, I don't know what all this means. I think RN means the number of, okay. I know this one. LStat is the number of low socioeconomic status people. Okay? People with low socioeconomic status, how many of them are in this neighborhood? So that significantly decreases the housing value. Okay, so that's so error term is 21.89. So now let's do a regression tree. Okay, it was a tree for regression purposes. Again, I wrote a tree, I pruned it back, I use it for prediction purposes, and the answer is 70. So now actually a tree is doing better than linear regression. Right? And here is our tree. We can plot it. Okay, so tree is the benefit of doing tree. Not random forest, not boosting, okay? Just single tree. The benefit of doing single tree is it's easier to look at the results and interpret it. Okay, so it tells me that LStat, low socioeconomic status, is kind of important. So it's the first variable to consider. If there's a large number of low socioeconomic status, we go here. If there's a small number, we go here. Okay. So as you can see, there's also low socioeconomic status, and there's NUX variable. There's room variable. Unfortunately, I really don't remember what they mean. Okay, so you can check the variable definition yourself. So. Anyway, so these are the predictions. Right. So if there are not many low if the number of low socioeconomic status people are low, and then if the number of rooms in the house is large, and then if the rooms in the house is even larger, then we get the highest prediction of housing value. But even if the number of rooms is larger than 7 but smaller than 7.5, as long as the DIS is larger than 1.9, then we still get a high housing value. Okay, so that's a prediction. Okay, so now let's try to back it, right? So remember the error term we have is 17 for tree, 21.89, 22 for regression, for linear regression. Now let's do back it. by bagging, I mean using all the variables. Okay, consider all the variables every time we split. So here we only have 13 variables. Okay, so I'm considering all of them, and our test error now go down to 10.99. Much better, right? Okay. What about random forest? So in random forest, I only consider 5 every time. We have 13 variables, but every time I split, I only consider 5 variables. And why do I decide on 5? Because I've already done the tuning thing. Okay. I've done the tuning. I choose the best number, and that's 5, and it gave me an 8.79 error. And finally, so this is the variable importance plot from random forest, but we'll take a look at it later. Finally, we do boosting. Okay. So again, these numbers have already been tuned. We use 10,000 iterations, 5 depth for each time, and the shrinkage, very slow shrinkage, 0.001, very slow. And in the end, we get a test error of 9. So in this case, our boosting is second best, random forest is the best. Can get the error down to 8.79. Bagging and regression to itself is 17, and finally linear regression is 21. So we are able to successfully decrease the error from 22, almost 22, all the way to 9. Okay, so which is pretty good, right, in this case. Okay. All right. So according to boosting and random forest, the most important variables are either room or LSTAT. So the most important variables for predicting housing value is how many rooms are in the house, obviously, and how many low socioeconomic status people are, like what kind of neighborhood is. Is this neighborhood full of low socioeconomic status, or is this neighborhood full of, without them, okay? So it seems that these two variables are the most important for predicting housing value in this data set. Okay, so let's do the partial dependence plot, right? So this is how housing value vary with low socioeconomic status percentage. The more low socioeconomic status percentage, the more housing value will decrease like this, right? Order from 0% to 35%. And this is how many the average rooms in the house. So it looks like it's also pretty discontinuous here. As if the house has less than 6 rooms, it's relatively low. But as long as we have more than 7 rooms, then immediately the housing price, the really should go up like that. Okay, so these are 2 simple illustrations, and we're done. Right? So that's all I want to talk about on tree-based methods. But we have for the last 2 examples. One is on classification, the other is on regression. Basically shows you the power and how to actually use these tree-based methods like random forest and boosting to achieve the best result. You got to tune it, but also there's also a way to interpret them, which is by looking at the variable importance plot and also plot the partial dependence plot. Right? The partial dependence plot is basically the derivative of f with respect to any variable by integrating over all the other variables. So that's how we produce them. In fact, because we have already finished this lecture, right? There's going to be new homework, but there's also some new challenge, right? And one of the challenge, there we go. So one of the challenge is indeed how to interpret nonlinear models. So like I said here, the model is for the linear model is very easy to interpret. It's beta 1, beta 2, beta whatever, right? You know that. But we have a general nonlinear model. In order to interpret the effect of x on y, we need to take partial derivative. Okay, given that in x2, I can take partial derivative with respect to x1, and I can calculate that. But the total effect of x1 is basically the integration of this one with respect to x2. Okay, you can do that. So this challenge is basically asking you to produce, where are we? Oh, I already closed it, sorry. Huh. I cannot find the model, but anyway, so I'm sorry. So the challenge is for you to produce the partial dependence plot. That's it. Okay? Remember we have the partial dependence plot? Right? There's a y, there's a certain x, some x, like the number of rooms in the house, right? And we see the relationship between housing value and the number of rooms in the house is something like this, okay? So this challenge is for you to produce a plot like that, because in our lecture slides, we are using a package, and we say, okay, partial dependence plot, create this, okay? Now, what I want you to do is not using any package, and just program yourself, and produce a plot like this. But in order to do that, it's not hard because you don't have to do random forest and stuff like that. Just do any linear model, right? Just do any linear model, simple ones, or even ones that you can calculate analytically what is the effect, right? What is the derivative, and then just do it, okay? Just plot it out. You don't have to do anything that's hard, okay? Right. Yeah. So try a linear model and try a non-linear model. But the non-linear model, let me see. So you can read it yourself. Cannot forget. But the non-linear model is, you can think about any simple linear model and then try to produce the partial dependence plot. Okay, so I think that's what the challenge is about. Okay.